Up to this point, we have studied one-dimensional kinematics in a fair bit of detail using vectors and graphs and a variety of other tools. In this chapter, we are going to study what happens if we have more complicated motions in 2 and 3 directions. Now, just because I say these are more complicated, they may not necessarily be much more complicated, and some of them are fairly straightforward to study. But the basic approach is fairly similar to what we did in one dimension. And so I had you watch a couple of videos of demonstrations of two-dimensional motion, and both of them showed the same concept in different ways. And that concept was that the motion in the x direction, y direction, and z direction are all independent of each other in usual cases. So we can take the x direction and we can make plots. We can consider the accelerations and everything in the x direction, and then we can ignore the y and z direction in that process. Then we can come back and consider the motion in the y direction, and when we're doing that we can ignore x and z, and so on. And so by considering each of the 3 directions independently, that allows us to understand the full 3-dimensional motion. So the basic idea here is going to be that we consider x, y, and z separately. And often it'll be just x and y. We don't always have to consider all 3. It just depends on what the situation is. So the way that we do that is by considering a position vector, and our position can change as a function of time, so I'll call that r of t, and that's really just 3 different one-dimensional motions, right? So that consists of an x coordinate, which also can change as a function of time, a y coordinate, which can change as a function of time, and a z coordinate that can change as a function of time. Okay, so this is one reason why we might use r sometimes for position and x sometimes for position, is it just depends on if we want to distinguish an x coordinate from the overall position. Just like we could with one-dimensional motion, we can find velocities in 2 or 3 dimensions by taking a derivative. So the velocity as a function of time is just dr by dt, which is itself a function of time, and that is an x component of velocity, which we'll often write as v sub x of t, and then there's a y component, v sub y of t, and v sub z of t. Okay, so position is a vector, we can split it into components. Velocity is a vector, we can split it into components. And likewise, acceleration is as well. So the acceleration, which can be varying as a function of time, is dv by dt, which is a function of time. And again, we have an x component of acceleration, a y component, and a z component. Right. So this works in all cases. This isn't an approximation or anything. We can consider the positions, velocities, and accelerations independently and then put them back together at the end, because this is just the definition of velocity and the definition of acceleration. Those are purely descriptive. We don't need to know anything about the forces involved or any of the other causes of motion. We're just describing what happens. And one of the things that is going to be most interesting to do in 2 and 3 dimensions is to consider cases where objects are turning. Okay, and this is going to be the approach we use when we're studying turning. Okay, remember that acceleration means a change in velocity in some amount of time, and that could mean speeding up or slowing down, which we studied before, but it could also mean turning, and we'll see how to handle that this week.